All right.
Well, good morning. And today I'm going to be talking about Arc Rock 23, which is a Nepheline-Sodalite syenite. So just an overview of what I'm going to be talking about. We're going to go over a brief introduction about the rock, the mineralogy, hand sample and thin section analysis, the formation environment of this rock, and then a little sneak peek at my second rock, an olivine basalt porphyry. So a Nepheline-Sodalite syenite is an intermediate silica undersaturated intrusive rock, and they can be medium to coarse grained, and in my case, this rock was coarse grained. And some of the basic mineralogy that we have, there are magnetite crystals, perthite, and perthite is feldspar, but it's feldspar with exsolution lamellae and or intergrowth of a second feldspar crystal. And in this case, well, I guess in general, really, you have a potassium-rich host or base feldspar with a sodium-rich exsolution lamellae or intergrowth. So for this rock, we have a microcline base, which is our potassium-rich feldspar, and an albite exsolution lamellae, which is our sodium-rich feldspar, and then as well as nepheline, sodalite, and hastingsite, which is an amphibole. So in my hand sample analysis was like, what can I identify in hand sample, really? And so what we can see is a white-gray feldspar crystals. These tend to be large lath shapes. Sodalite, you can't really tell unless you have a black light, which if you guys remember back to when we first identified these rocks, we had one that fluoresced orange, which is this Nepheline-Sodalite syenite, and it's the sodalite that is actually fluorescing. There are black magnetite grains, which were easy to identify in hand sample, but the nepheline and the syenite and some of the feldspar just became a bluish gray color, and you couldn't tell which crystal you were looking at. And there are very few amphibole grains in this rock, and you cannot see them in hand sample. So then we have the per alkaline minerals, which, as Izzy mentioned yesterday, means that we have more of our alkali elements, so our calcium, potassium, and sodium, that more of those elements than our feldspars can absorb. And so, because we have these really high alkali contents, we start getting feldspathoids along with our feldspars. And our feldspathoids are our nepheline and our sodalite. And then here is our miscibility gap feldspar triangle. So as you can see, we have the microcline here and the albite, and they meet here in this miscibility gap where they start unmixing. And then our IUGS classification, the Nepheline-Sodalite syenite that I'm looking at kind of goes between this Foid-bearing alkali feldspar syenite and this Foid syenite as it transitions from a syenite into our Nepheline-Sodalite syenite and then back into a syenite as a sequence of magma intrusions occurred. So here are some hand sample pictures. So as you can see, you have these big, long white laths of feldspar. You can see some of the grayish blue almost looks like a ground mass, but it's actually just large crystals of feldspar, sodalite, and nepheline, some of which are intergrowing with each other. And then the black crystals here are our magnetite grains. Just another picture of the top of the rocks, you can see the coarse grain texture. So then section analysis, basic identification, and then the difficult task of distinguishing the feldspar from the nepheline. So the easiest thing to identify are the opaque minerals, which in this case is our magnetite, and then the isometric minerals, which are isotropic. And when you put the upper polar in, they are extinct for 360 degrees. And that is the sodalite. So it made the sodalite very easy to identify once I put the upper polar in. And then for feldspar and nepheline, they are pretty much exactly the same color, and they both have brown halos, or there's a brown halo that surrounds the feldspar when it comes in contact with the nepheline, and sometimes that brown halo can be on top of the nepheline. And the only reason I was able to tell them apart is that the feldspar all has Carlsbad twinning or exsolution lamellae, and of course our nepheline does not have that. So here are my thin section drawings. Obviously, the magnification in the picture is a little bit more than on my drawing, but you can see this large magnetite crystal in the middle as a reference. And pretty much with the plain polarized light, the only thing you're able to see is magnetite and the brown halos from the nepheline and feldspar. So you can't really tell much, except for this crystal here is a Hastingsite. Looks very similar to biotite, but it is an amphibole. And then here's the picture with the upper polar in. Again, you have this large magnetite as a reference point. You can see the feldspar with exsolution lamellae and Carlsbad twinning in this particular crystal. Here we have the brown halo as it comes in contact with a nepheline. I don't know if there's any sodalite in this picture, but on my drawing, the sodalite has been outlined in Sharpie because otherwise it looks exactly like magnetite. And this one is just to get a better picture of this really high birefringent spot that we see in this rock. And it doesn't make sense because none of the minerals that are in this rock have a high birefringence. And it's more of an interstitial type of rock or mineral, so we can tell that it probably didn't form in the magma and that it's probably a secondary mineral that happened to either intrude into a fracture of the rock with water, or it was eroding into the rock and eroded minerals and just filled in the space. And so this mineral, me and Dr. Wolf looked at it and we realized it had a second order birefringence and decided to classify it as a secondary mineral and possibly an alteration of mica. So the formation environment, just gonna go over the location, the age, and then the tectonic setting. So this rock was located in Red Hill, New Hampshire, and it is part of a series of ring dikes. And these ring dikes form a chain. So right here we have Red Hill, and then you see the Ossipee Mountains that you see little intrusions that go into Maine. And those are all small ring dikes from presumably the same magma, which also forms this White Mountain magma series. So the exact age of this rock is unknown, but we do know that this right here is our Nepheline-Sodalite syenite, and we know that it is younger than this coarse syenite that it intruded into, and that it is older than this fire tower syenite, and then the granite and quartz syenite that are also have intruded. It is predicted that this series the whole series goes from the Permian through the Cretaceous, but the Nepheline-Sodalite syenite is predicted more Jurassic to Cretaceous as Pangaea was drifting apart. And the reason that the age is unknown is one, this series of rocks, especially the Nepheline-Sodalite syenite, they make up 2/3 of 1% of all the rocks in the White Mountain magma series. So there are not a lot of syenites in this region, and because of that, they're not studied very well. And a lot of the research is from the 1930s. So when this magma series intruded into the Devonian rocks, they were saying that the magma must be Devonian or Carboniferous in age. But now that we know about plate tectonics, we do know that it is more likely Mesozoic in age because that's when we start seeing rifting events that would create magma. So ring dikes. Ring dikes are concentric rings formed by magma intrusions, and in this case is not Red Hill, but I like the cross-section views that they show. So you can see in map view, this is two concentric circles that intrude into each other, and in cross-section, you can see that this light gray ring intruded up to the surface, and then a secondary intrusion of this dark gray magma intruded through that first ring. And this most likely happens when the first rock is still hot, because they don't see a lot of fractures, and they more see like almost a strain of this new magma rising up through a hot, cooling rock. And I already mentioned this, but The tectonic setting was the rifting of Pangaea, which formed active volcanism in the region, which formed the ring dikes. And in this region, the ring dikes are actually the magma chambers of the active volcanoes, so we see a lot of the coarse-grained rocks. And for Red Hill, we see the intrusion of alkali and feldspathoids magma, and it gradually gets more silicic. And the magma formation, so we have a differentiation of magma. The first intrusion in this region is this dotted one. It's the outer core syenite. This syenite doesn't have the feldspathoids that the Nepheline-Sodalite syenite does. And then it goes to a phoid syenite, which is our feldspathoids. We see the nepheline and the syenite. Again, and then we get another magma intrusion that goes to a syenite. And then into this little area, we have a quartz syenite and then a granite. So if you remember back to the IUGS classification, we went from the phoid classification, which is no quartz, to having quartz and eventually an overabundance of quartz. So we go from silica undersaturated to silica oversaturated through magma differentiation. And for the phoid syenite, the magma had a high volatile content. And we can tell this because the presence of the feldspathoids is very odd, especially in this region, to only have one ring with these feldspathoids. So they believe that these feldspathoids were introduced into the magma chamber through liquid content that was high in chlorine and other alkalis. And this alkali content and chlorine content allowed for additional crystallization of nepheline that wasn't predominantly magma related, and the crystallization of sodalite because sodalite has chlorine in it. And as these these magmas were intruding, they were assimilating more syenite and alkalis and eventually quartz, because out here in this white area, we have a quartz diorite. So this quartz syenite probably assimilated much more of the quartz diorite than some of the other rocks. But we have a contamination of the magma as it assimilates, and it absorbs more potassium and sodium from the rocks that have already intruded. So here is a nucleation and growth curve that I created. And I didn't have a picture of it, but in thin sections, sometimes you can see magnetite crystals growing that have grown, and then other crystals have grown around the magnetite. So we determined that the magnetite formed first, and there's not a lot of iron in these magmas. So what happened is that these magnetites formed and drew all of the iron and the iron oxides out of the magma, driving the magma composition more alkali rich. And then there's the nepheline. And the nepheline we know formed before the perthite because we see those halos where we can see that the perthite has actually started growing over and into already crystallized nepheline. And these nepheline crystals can actually be kind of big, so it has a lower nucleation and a higher growth curve. And then the perthite are feldspars, very large laths. Some of them were longer than my thin section screen, where I would have a whole feldspar going across. And so again, a lower nucleation and a higher growth curve. And then the sodalite formed last because it was from a water or fluid intrusion rich in chlorine and feldspathoids. And after seeing Andes, I probably should have done this, but because of that feldspathoid rich liquid, we would probably see this nepheline curve having another rise over here when the sodalite starts forming, when we actually get that content of feldspathoids enriching the magma. So this magma composition, I have our triangle here with our alkalis, iron, and magnesium. As the magma formed, it is believed it came from a basaltic magma at the upper mantle and lower crust, and we would have seen for our Nepheline-Sodalite syenite a fractionation of the olivine and the pyroxenes from the original magma, driving our composition towards the iron. And as we see our magnetite crystallize, it drives it right towards alkali, and we get these alkali-rich magmas. This picture on the right is of the whole Red Hill series. So the oldest rock is our coarse syenite. We see this weird dip in a feldspathoid-rich magma, and as we see, it only occurs in the Nepheline-Sodalite syenite, and that is why it is believed that a fluid content brought these feldspathoids to the magma. And then we see it transition back into this microperthite zone, which is our Fire Hill syenite, our quartz syenite, and then our eventually granite when we get that plagioclase starting to form. And the phase diagram. This one had me confused for a bit because of the exsolution lamellae. And my first thought was to draw our tiki diagram because that's where we see exsolution lamellae forming. But as I started reading more about this, with the water content in this magma, it is wet, and our Pikachu diagram shows wet magmas, and as well as it had to form at depth because of otherwise the temperature to actually melt the country rock and form this syenite would be way too high, and the magma would not have reached that temperature. So here I have a liquid forming, and as it comes down here, it fractionates. And so this part of the liquid in orange is left behind, and that's going to become our syenite magma. And this right here is obviously, it hasn't reached this solvents yet. So we are in this zone and we can get the exsolution lamellae to start forming in some of our feldspar crystals. And then these are my references. And then this olivine basalt porphyry, it's a porphyritic rock with a fine-grained ground mass with olivine, augite, plagioclase, and magnetite. The olivine, augite, and plagioclase form phenocryst as well as the entire ground mass. But I am also arguing that this is an alkali olivine basalt instead of just an olivine basalt. And so my thin section drawings, again, you have this Texas-shaped magnetite crystal for reference. You can't really see the augite phenocryst, but here's a plagioclase, and then this really fine-grained ground mass that was very difficult to draw. And in this picture, you can see the augite phenocryst there, as well as mainly feldspar ground mass. And any questions?
Abby, I have a question for you.
Yeah.
You did like an insane amount of research. How did you know like where to turn to after your like sheet didn't turn up with much?
There's not a lot of research on these type of rocks. Nepheline syenites are rare, and then Nepheline-Sodalite syenites make up very few rocks. And so pretty much there were two main references. One was the original person who collected the rock, and then one was a more recent page or a recent article, I think it was the late 1960s, where they actually had more information on magma fractionation and then obviously the understanding of plate tectonics. But a lot of it came from me just having that little bit of background information, researching what the tectonics were like in New Hampshire, and then a lot of inferencing on what could have happened.
All right, thank you.
Any other questions? Did you come across any mention about a thermal divide that might have tipped the differentiation path toward the Floyd versus the quartz cyanites?
I did not, but there were a lot of like hypotheses on how those voids got into the magma, and one of them was it being a thermal divide and the sodalite being a magmatic mineral. But like I didn't really understand how, but I guess it was looking at more of how interstitial the sodalite was, and it was determined that it was most likely not a magmatic mineral, and that it came from some sort of outside source of water.
Damn open system.
Actually, the sodalite and the feldspar is very pure, so they don't think it was, or the water obviously makes it open, but the rest of the like there was nothing that caused impure minerals in this rock, which very interesting and very confusing to read about.
All right. Good job. Thank you.